Pluto, a far-off and confounding, more unassuming planet, was once an individual from our nearby planet-gatherings planetary family. Anyway, later upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They recommend that this cold world is on a potential crash course with Neptune. Anyway, how should this work out, and what might be the consequences of such an enormous occasion? Are we seeing an exciting huge quirk? Or is there another thing to this oncoming boundless mishap? Join us as we investigate the possible consequences of a Pluto-Neptune crash. Pluto, a previous planet that was cut back to a dwarf planet, generally due to its unpredictable circle, stays a subject of interest and study in the huge academic community. As indicated by later assumptions by leading subject matter experts, Pluto's direction is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a possibly perilous impact between these two planets that could be a huge danger to Earth. But how is such an event even conceivable? Pluto's excursion around the Sun is not normal for some other planet in our solar system. It requires a stunning 248 years to finish a single circle. This implies that since its discovery in 1930, it hasn't even finished one full revolution. Anyway, the interest doesn't stop there. Pluto's way is marked by its astoundingly circular shape, standing out totally from the almost round circles of the major planets. What makes Pluto's circle significantly more abnormal is its tilt, set at 17 degrees to the ecliptic plane. The way Pluto follows is considerably more inclined compared to the other planets. This slant and whimsy add layers of intricacy to its orbital design. One of the most dazzling parts of Pluto's circle is its combination with Neptune's. For around 20 years in each circle, Pluto actually moves closer to the Sun than Neptune, challenging what we could anticipate from their positions in the nearby planet group. This leads to the natural inquiry: why hasn't Pluto collided with Neptune? The response lies in the gravitational impacts of other planets. The investigation of Pluto's circle started not long after its discovery. Initially, stargazers attempted to understand its surprising way. Dissimilar to different planets, whose circles lie somewhat near the ecliptic plane, Pluto's circle juts with its steep tendency and odd shape. The mystery grew with the acknowledgement that Pluto's circle, in fact, does cross Neptune's. The stability of Pluto's circle amidst these intricacies is evidence of the complexities of heavenly mechanics. The three-body issue in space is about sorting out how three objects in space, like Pluto, Neptune, and the Sun, move and impact each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on one another. For Pluto's case, this issue shows how its circle, Neptune's circle, and the Sun's gravity all interact in a complicated manner. Terms like astrometric libration and degree libration, along with the VSK precession, are part of this riddle. As indicated by astrophysicists, what keeps all planets in their circles is a sort of libration. As for Pluto and Neptune, this term truly implies that when Pluto crosses Neptune's circle, its position is continuously somewhere around 90 degrees from Neptune. This spatial detachment is pivotal in keeping their circles from impacting. Degree libration, on the other hand, alludes to the upward movement of a celestial body in its circle. For Pluto, this implies that when it comes closest to Neptune or some other giant planet, it is situated far above their orbital plane, giving an extra layer of security from possible crashes. One more critical figure in this situation is the VSK precession. This is named after three researchers, VAV Apple, LV, and Chi, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling influences how they move. For Pluto's case, VSK helps us understand why its circle around the Sun is so weird in spite of the obvious tumult. This precession helps keep Pluto's circle stable for an extraordinarily significant time frame. The VSK precession shows that, despite the fact that things in space could appear to be wild and sporadic, certain patterns and rules keep everything in place. These elements help keep Pluto's circle stable, ensuring it doesn't collide with Neptune or drift off course. This three-body issue helps us comprehend how these circles evolve because of the way space objects pull on each other. Concentrating on this helps us learn more about Pluto, our planetary group, and far-off stars and planets. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's circle is, in fact, unpredictable, with minor deviations in starting conditions leading to huge differences over thousands of years. Anyway, these whimsical properties of Pluto's circle have been found to maintain stability over long time scales. Continuous simulations have helped, in fact, us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's circle around the Sun. Neptune has an exceptional relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's circle stable. Anyway, Neptune isn't the only one helping. Jupiter's gravity also plays an enormous part in safeguarding Pluto's circle. Also, Saturn helps too. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an extraordinarily long time, maybe even billions of years. Maybe Neptune, Jupiter, and Saturn are cooperating to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are significant in the larger context of the universe, as they help keep the control and consistency of celestial body movements. Without these factors, our solar system would be a place of much greater disruption and unpredictability. Bodies like Pluto could potentially collide with others or be launched out from their stable orbits, leading to a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it possibly affecting Neptune later on, understanding its circle is fundamental. This gives us a clearer picture of the planetary group's dynamic nature. The situation of Pluto shows how even the most apparently unstable orbits can achieve a condition of equilibrium through the complex cooperation of gravitational forces and orbital mechanics. It also illustrates the importance of continuous observation and investigation of these phenomena to better grasp our place in the universe. Understanding the depths of space frequently leads us to confront the surprising nature of celestial bodies, and Pluto's circle is an ideal illustration of this unpredictability. The idea of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been extraordinarily helpful for researchers to figure out how Pluto moves in space. These simulations use complex mathematics to show how Pluto, along with other space objects like Neptune, pull on one another. By changing small details in the simulations, astronomers can see how even tiny changes can have a huge effect on where Pluto ends up. In the late 1980s, these simulations revealed something really intriguing about Pluto's circle. Regardless of having features like astrometric libration and degree libration to stabilize it, its orbit can still be turbulent and inconsistent. If you start with even a small difference in where Pluto is or how fast it's moving, its path can end up looking completely different. Anyway, despite this chaos, Pluto's circle remains stable for an incredibly long period, billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it might seem wild at first. Predicting significant events, particularly when they involve violent orbits like Pluto's, presents enormous challenges. The inherent eccentricity of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide solid foundations to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive abilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to vastly different outcomes, making exact forecasts a daunting task. Besides, the turbulent nature of celestial orbits like Pluto's reminds us of the ever-evolving, dynamic nature of the universe. While we've made tremendous strides in understanding space, the case of Pluto reminds us that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can sweepingly affect the stability and direction of other bodies within the system. So why are leading astrophysicists just now raising concerns about a potential impact between Pluto and Neptune, despite all these intricate forces working to prevent such an event from happening? Neil deGrasse Tyson, a famous astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers clever commentary on the evolving nature of celestial mechanics and the public's fascination with the overlooked corners of space. Tyson's position on Pluto's renaming is grounded in the continuously expanding knowledge of our solar system. He sees the renaming not as a downgrade, but rather as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and transformation. He sees Pluto's orbit, as well as its relationships with Neptune, from a perspective that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the distant future due to the ongoing gravitational interactions between it, Neptune, and the other planets. In conclusion, Pluto's orbit is a fascinating case study in the intricacies of celestial mechanics and orbital dynamics. While current scientific understanding suggests Pluto is unlikely to collide with Neptune, the future remains uncertain as space exploration and our understanding of gravitational forces continue to progress. We may gain further insights into the long-term behavior of these distant bodies. Until then, the mystery of Pluto and its potential future interactions with Neptune will remain an intriguing subject for astrophysicists and space enthusiasts alike. As we continue to study Pluto's orbit, it is clear that the factors affecting its path are far from simple.